Okay, so I'd like to look through some examples of doing antiderivatives in which the function that you're trying to take the antiderivative of will give you one of our inverse functions, inverse trig functions. And you'll notice that there's really only three because the way that arc sine and cosine are paired together, just off by a negative, arc tangent and cotangent paired off by a negative, arc secant and cosecant paired off by a negative. So what we're really looking for is antiderivatives that have this structure. Maybe a difference of squares or a sum of squares, another difference of squares with another value or variable outside. Those are the characteristic antiderivatives that we'll evaluate that will give us arc cosine, arc tangent, and arc secant. And we don't have to worry about the other three because they would just have been off by a factor of -1. So that's what we're looking for. So we'll go through a couple of examples, and they do start off, I think, rather easy. And they almost start off so easy that you might think, well, maybe I don't need a U substitution. But I still think it's smart. I still think it's good to get in that habit of what's your U, is your du okay, and then what value is a in these kinds of problems. Again, I'm looking at this characteristic square root. Notice that I can't just let u equal 9 minus x squared, because if I try to let u equal 9 minus x squared, its derivative is -2x dx. The -2 I can manage, but that x I can't. This is off by more than 1 degree. A derivative only takes you down 1 degree. So I know this is not a simple U substitution. And so then my hope is that I realize, wait a minute, this is the characteristic format of inverse trig. I'm going to let U equal just the x, and my a value is 3, because 9 is 3 squared, and then therefore my du is just a dx. So this is perfect. This I could rewrite if I wanted to as the square root of 3 squared minus u squared. Oh, sorry, I have the du. Du. And again, maybe I don't need a u substitution, but I want to make sure I realize that this is inverse sine. Inverse sine, a squared minus u squared, square root it. So the antiderivative, notice this is the one that does not have 1 over a. It's just arc sine of u over a plus c. In this case, u was x and a was 3. So arc sine of x over 3 plus c. And I probably spent more time on this one, and this is a very simple problem, more time than I really needed to, but I want to stress why you cannot let this whole denominator be your u, because you don't have the right derivative. So we have to get good at recognizing this is an inverse trig function. Same thing here. I notice I'm quadratic in the denominator and not linear in the top. It's just a constant, just a 1. And again, I can't let that whole thing be u. Maybe that's what I'm used to, because my derivative is 32x dx. I only have a dx, so I can't do that. So I need to recognize that this is a u substitution that is needed for inverse trig. And the absence of the square root tells me it's going to be tangent. So I'm thinking, what is squared here? Well, let's let u equal 4x. And that's, again, 4x as a quantity squared would be 16x squared. The derivative is 4 dx. So now I am glad I used a u substitution, because I'm off by a factor of 1/4. And then 1 squared is 1, so my a value is 1. So I can rewrite this as the antiderivative of 1/4 of 1 over 1 squared plus u squared du. And this is, again, this is the characteristic shape or structure of arc tangent. So we have 1/4. Now arc tangent comes with a 1 over a. So I'm going to put that 1 over 1 just to emphasize that I know that that's there. And then I have arc tangent of u over a, which is a 1, plus c. And then go back and figure out what your u is. U is 4x. So I could say this is 1/4 arc tangent of 4x over 1, which is just 4x, plus c. Okay? Next problem, again, to stress, to emphasize, This can't be my whole u, because a 10th degree would come down to a 9th degree, and I have a 4th degree. So my next strategy, if u substitution doesn't work, is this a inverse trig function? Does this have the structure that would fit? And I'm looking for squares, and x to the 10th is actually x to the 5th squared. So that becomes my u. So, oops, I said it right, I just wrote it wrong. So let u equal x to the 5th, du is 5x to the 4th dx, which actually is a perfect u substitution. And my a value is equal to 4, since 4 squared is 16. Now this, I need to have it in terms of recognition. This is inverse sine. So inverse sine is 1, well actually I should have 1 over square root of a squared minus u squared du. And inverse sine, or arc sine, does not have a 1 over a. There's no extra factor for my dx here, so in terms of converting. So it's just arc sine of u over a plus c. And as you get good, you could substitute your u and your a simultaneously. So this is arc sine of x to the 5th over 4. X to the 5th over 4 plus c. Okay. So hopefully this is making sense. The next one, well, I guess by process of elimination, it's probably gonna be arc secant, because we haven't had one of those yet. And it is, I want you to see that we have an extra variable out here. We have a squared. Notice it's variable squared minus constant squared, as opposed to the other order, which is arc sine. So in this case, I'm going to let u equal 2x, and then du is 2 dx, so we're off by a factor of 2. So I divide that over. My a value is 5. And what I have to be careful of is that I want, if you look at your inverse secant, you want u squared. And right now, I have, this will be u, so I have 1 over u squared minus a squared, but this x is not an automatic u. In fact, the x is actually equal to u over 2, right? If u equals 2x, then u over 2 is equal to just 1x. So I have to be really, really careful. This x is really going to be a u over 2. So u over 2. So just be really careful. And I really want to make sure that I'm integrating this correctly. This u over 2, this 2, it's a fraction divided by a fraction. So that 2 is actually going to flip up, and it's going to cancel that 1/2. So this 2 is a 2 over 1. We still have the 1/2 from our u substitution as a derivative, and then we get 1 over u square root of u squared minus a squared. So be very careful, especially when this variable and this variable aren't a 1-to-1 ratio as they were here. So then those cancel, and I'm just integrating this. These cancel, these cancel. So when I integrate that, we do get a 1 over a arc secant of the absolute value of u over a plus c. And so then our a value is 5, so we get 1/5 arc secant of the absolute value of u, which we said was 2x. We definitely need those absolute values over 5 plus c. Okay, so